Let's take a look at another example. This is about a car with the initial velocity and a deceleration of a. Say, if a car has initial velocity, after apply a deceleration, it will stop after 3.6 seconds. So the very same car travel at the very same initial velocity to the right, and there is a dog L meters away from the starting point of the car, let's say. So obviously the car will apply the brake, the driver will apply the brake, and the car will decelerate at this constant. And after 1.7 seconds, the car reaches the location of the dog and fail to stop. And the dog is smart enough to jump away. So under the same deceleration, the car actually moved another 3.8 meters and finally stopped. V final equal to 0. Stop means that speed equal to 0. The question is, what is the initial velocity of the car? What is the deceleration rate of the car? And what is the distance between the car and the dog initially? So we ask the question of what is V initial, what is the rate of deceleration, and what is L. How do we solve this problem? Well, sometimes that we have to just list equations according to what we know, and then we combine them, then we solve them together. So it is very important to have a diagram and also play the sequence. When that happens and we apply the proper equation, and we will get there. Okay, let's take a look. The first condition is with such initial velocity, with such an deceleration, the car stops, which means V final equals 0 at 3.6 seconds. So I think we should use V final equals to V of initial plus a t that equation, because that's what involves. So let's say V final 0, initial is unknown, but let's choose initial direction as positive. So it's V initial, positive. And since the acceleration is opposite, so it's negative of a, and t 3.6, equation number 1. Condition number 2 says that with same initial velocity, same deceleration, after 1.7 seconds, it traveled L meters. So I think we should do delta x, change of position, equals to V initial of t plus 1/2 of a t squared this time. So delta x is change of position, and obviously this initial, this final, our change of position is positive L. That's right here. Initial velocity is the same initial. T this time is 1.7 seconds. 1.7 of second. And we apply the deceleration. A is negative, so it's negative 1/2 of A. And T again 1.7. And don't forget about this squared. That's equation number 2. So we have 2 equations, but we have 3 unknown. Because if you take a look, we have initial velocity, we have the rate of deceleration, we have that L. However, we do have the third condition, which is after it travel L, another 7.8 of meters the car stops. So what we can do is, actually, we know the final is 0. We know the initial is that. We know the total displacement is this. We know the deceleration. So what we can do is, actually, we can apply that one. V final square minus V initial square equals to 2a of delta x. So final is 0, initial is that the very V initial, but don't forget squared, equals 2, be careful, the entire L plus 7.8 meters, the acceleration is the deceleration, that's why it's negative a direction, and then delta x is L plus of 7.8 is positive. Now be very careful, I mentioned before, here final velocity, initial acceleration, and displacement, these are all vectors. You really have to choose a direction, say to the right is positive, then opposite direction will be negative. When you plug in the number, you have to make sure that, for example, when I think about this A, because it's that direction, it's negative. Then this A become only the magnitude. And same thing here. Here's A, it's minus, it's negative. This is magnitude. And see, V initial is positive because it's moving towards this direction. And delta X, because starting from here to the right, that's positive. That's why it's positive L, and positive L plus positive 7.8. The square part, we don't have to worry about it because it's squared. So therefore, we have equation 1, 2, and 3. We have 3 equations, 3 unknown, and I'm very sure we can solve this. So sometimes we just draw the diagram, follow the condition, and list the equation, proper equation, and then we just combine them and solve it. So sometimes it's a complicated issue. It's not just one stop or one step that we can solve everything. The next topic that I would like to discuss is the freely falling objects. That is a very common phenomenon because we know that if we do not hold something tight, we let go of it, it's going to drop. Well, that is actually because the Earth pulls everything down towards the center. But obviously, when the object hits the ground, it just speed gets reduced and just stop. So let's have this definition clear. Freely falling objects. First of all, freely. What happened is, imagine we have an object of mass m. Say if we just hold it and let it go, in that case, initial velocity equals 0. We could have tossed it up. The initial velocity will be up with some magnitude. Or we can throw it down, then the velocity has a direction down and with some magnitude. But if we just say let it go, well, if initially is at rest, that means VO equals 0. Okay, what happened is Earth pulls it down. Because Earth pulls down, later you will learn, well, from the motion equation that you can see, for example, V final equals to V initial plus AT. This is what we call kinetic equation, kinematics, because it's simply just say, oh, if you have initial velocity, or if you have acceleration or deceleration, something, and your velocity will change after t second. So let's think about here. If your initial velocity is 0, obviously when the object falls, let's say it falls distance by h, it will pick up some v. Let's name that v as v final, for example. So if initial 0, final v is something, which means you do have an acceleration because you pick up the speed. Obviously this time the acceleration is down, and that special acceleration will give a symbol as g because we name it, it's gravitational acceleration. It's called. Well, because we can have acceleration from the car's engine or something else, manpower, but in order to separate that from, it is because the Earth pulls. So we name this acceleration as gravitational acceleration. This is an acceleration, and obviously it will be in meter per second square. And later in physics 1b, you will be able to learn that near the surface of the Earth, this g is very close to a constant. As a matter of fact, the magnitude of that g is very close to that 9.8 of meter per second squared. So it's a constant. What does that mean? That means every 1 second, the object will be able to pick up 9.8 meter per second of speed increase. But only this is under condition it falls freely, which means without air friction? Well, you see, if everything accelerates down with the same rate, then if we release a leaf and a piece of stone at the same height, supposedly they will hit the ground at the same time. But obviously it takes longer for the leaf to reach the ground. That is because the cross-section of the leaf actually encounter a lot of resistance, air resistance. That air resistance compared to the weight of the leaf, which is the Earth's gravitational pull, is significant. Therefore, the acceleration downward on the leaf is much, much smaller. On the other hand, the gravitational, I should say, the air friction on the object, on the stone, maybe is also large, or even larger. If you can have a piece of big stone, so the cross-section area of the stone is big. When the stone moves down, occupy the space underneath, it has to push the air away. The air will push it back, so the stone get a very big air resistance. However, if that force is much, much smaller than the weight of the stone, and then the stone will still have significant downward acceleration. So freely means we ignore the air friction. So we just say no air friction. Well, that is true on the surface of the moon. That's why when astronaut Armstrong landed on the moon the first time, the first experiment they conduct is they drop a hammer and a piece of feather. And both of them release both of objects from the same height, and they hit the ground surface of the moon at the same time. Because on the moon there's no air, then there's no air friction. So freely means no air friction. Well, we'll ignore that. Falling. Oh, let's talk about that. Well, you see, we can release an object with initial velocity equal to 0, and because of the gravitational acceleration downward, and this object is going to pick up downward speed, that's called v1, and then a longer arrow means larger amplitude, so that's called v2, and then let's say v3. It is falling, obviously. However, as a matter of fact, if I tossed something up, let's say initial velocity is up, it's still falling. You know why? Because you see, this g, once the object leaves your hand, this g is there. So just like a car has initial velocity up and the deceleration is downward, so this v initial, well, will be reduced. So if I draw the arrow, it will get shorter and shorter. So at the highest point, which is the peak, that the v equals to 0. Then what? The g is still there. So the object will start to accelerate downward. So the arrow will get longer and longer and longer. So during the whole process, even the stone goes up, coming back, it is falling all the time because the g is always downward. It is always there. Well, if we threw something down with this v initial, and if it's downward, then compared to case number 1, it will pick up the same rate because g is every 1 second it's going to add up 9.8 meters per second. For example, this one initial velocity equals 0. So after 1 second, let's say v1, that is 9.8 meters per second down. That's the speed. But if with initial velocity, let's say 10 meters per second down, at t equals to 0, well, after 1 second, this one's going to increase another 9.8 meters per second. So then this v1, after 1 second, it will be 19.8 meters per second. So it is falling. So all three cases, doesn't matter what's initial velocity, the object is falling because the gravitational acceleration g is always there. Now let's take a look at how do we apply what we learned of one-dimensional motion. We have 3 equations. One is about change of position, initial velocity, acceleration time, and the other is final initial velocity, acceleration time, and then the other one without time. How do we apply this to y direction? See, This is our y direction. As a matter of fact, you can either choose up as a positive or down as a positive. It's totally up to you. So this is a one-dimensional motion with most of the time that we put y equal to 0 on the ground or on the reference level that we pay attention to. For example, if the object starts from the tabletop, we say, okay, tabletop is y equal to 0. So you can choose any reference point as y equal to 0. Then you say, oh, let's say up as a positive. But if you throw something down, your initial velocity is down, your acceleration is down, everything down, there's no point you set up as a positive. Then you say, okay, down is positive. So it's totally up to you. When we apply this equation to the y direction, we better just say delta y equals to v initial y t plus 1/2 ay t squared. So we just translate everything to y. V final y squared equals to v initial y squared plus ayt. So probably you will say, why we do this? We just remember that's why we don't have to translate. Well, you know, from chapter 4, we will have both x and y involved. So we better just tell people when we solve a problem, we apply this equation. This is the constant acceleration motion equation. We apply these to the y direction. So we better tell people that's y direction. So that is about we're going to use the equation we learned to solve some problem. Now let's solve a very simple problem. Say, if we toss something up from the ground with v initial y equals to, let's say, 20 meters per second. The question number 1 is how high it will go. So, well, basically, let's say this is the peak. This is the height. The reason we say this is the highest place is because it's not going up anymore, which means v here. So here, maybe it's not final because you start from here, point A. Then this you can name point B, because when the object reach here, that is only the second point you want to pay attention. Then the object start to fall back. So imagine that I just simply want to let you see this. So as a matter of fact, if it's going up without wing, it will coming down on the same vertical direction. But now I just draw up here, down there, so you can see clearly. So let's say we define before the impact that point as point C. It's very important that we define before impact, because only when the object is in the air that it's subject a G, remember, free falling? Only free, which means ignore air friction, it's still in the air, then acceleration will be G. It's downward, magnitude is 9.8 meters per second square. So the question number 1 is how high? So maximum height. Second question is how long does it take to go up? How long does it take coming down? And the third question is what's the total time? Probably was it's funny. If we know how long take it up, how long come take it down, then I know the total. But we will apply different technique. We probably solve T up, then we solve T total, then we find T down. It's very, very interesting. Say, for example, if we want to find the height. I say because we know the height is between A and B. See, for this equation, it has initial, final, initial, final. You can choose any 2 points, one as initial, the other as final. So we can apply our equation. First, A is initial, B is final, because we're interested in how high does it go. So if we know V initial, which is right here, we know V final, which is right there, because VB equals 0. And we know the deceleration. We're not interested in time. We want to know the displacement, because initial to the final is displacement. I think we are safe to choose this one because we don't want time involved. So you see, our final is VB. So VB squared, that's final, minus initial is V initial Y. V initial Y right here, squared, equals to 2 be careful in this case, because even though here squared you don't have to worry about, but you still have to choose which way is positive. Because look at this, here's delta y. Delta y is a change of position or displacement. Your displacement is up because initial is here, final there. So if you choose up as a positive, say, then down will be negative. So 2ay is negative because it's down. Value is g. Delta y is your h. Is positive because it's up. So knowing that vb squared equal to 0, so you have v initial y is given and g value is given. Therefore, your h negative cancels equals to 2g v initial y squared. See? So how high does it go? Really depends on how big is the initial velocity up and how big is the Earth's gravitational pull, which is the gravitational acceleration. So if we go to the moon, guess what? G on the moon is only 1/6 that of G on the Earth. So if G on the moon is smaller, if you tossed something up like this, same v initial y on the Earth and the moon, but because G on the moon is 6 times smaller than G on the Earth, the h on the moon will be 6 times bigger than on the Earth. So you can jump much higher. Okay, we solved the maximum height. Now let's have fun to solve the total time. Well, you see, in order to solve time, we can choose this one and that one. If we want to solve total time, well, the initial is A. The final is C because it's from here to here. That is initial. C is before the impact. So, right before impact, A and C are on the ground level. So, this is a very good choice. Why? Because look, if we choose A as initial, C as final, because we're talking about y direction. Their y position is all, if we take the ground as y equal to 0, then your delta y is 0 minus 0 because both A and C are on the ground. Well, a little bit above the ground, okay? Your v initial y is positive because it's up, v initial y. T plus 1/2 ay is the acceleration that is down, it's negative, value is g, and t gets squared. Look at this. Both sides of the equation I can divide by t. So actually 0 divided by t is still 0, and this t cancels, so that equals to v initial y, and one of the t cancels, that's minus 1/2 of gt. So it gives us the total time of this round trip. T total equals to twice of v initial y over g. So you suspect that going up is v initial y over g and coming down is another. That's why the total is twice of that. Actually, that's absolutely right. Why? Because look at this. If we apply, here we go. I think it should be v final equals to v initial plus at. That equation. Okay, it's not. So if we apply this equation from A to B, final is here. It's 0 because the highest point. So final is 0 equals to initial, that's positive, v initial y. Ay is minus g. This t is t up. Why? Because A is your initial, B is your final. See, our final y is 0. Look at this. Your t up is v initial y divided by g. So look at this. This is total. V initial y divided by g twice. That's total. So up and down, it takes the same time. Very interesting.